I'm going to be talking about properties of real numbers. First, I should say what real numbers are. Every number that you would encounter in everyday life is a real number. In fact, if you look at a number line, every point on that line corresponds uniquely to a real number. Here are a few examples. -1 is a real number, 0 is a real number, square root of 7 is a real number, even pi is a real number. Now let's distinguish between two different kinds of real numbers. Some real numbers are what's called rational, and some are irrational. What it means for a number to be rational is that it can be written as the quotient or a fraction of two integers. So 7/12 is a rational number since it's a fraction. -8/3 is a rational number. And of course, any integer is rational, like 6, because 6 is equal to 6/1. What are some examples of numbers that aren't rational? What about the square root of something which isn't a perfect square? The square root of 2, for example, is an irrational number, since it's not rational. Pi is also an irrational number. This is because there's no way to write either of these numbers as a fraction, at least not a fraction of integers. Another way to tell whether a real number is rational or not is to look at its decimal expansion. For example, take 1/3. This is equal to 0.333, and then it repeats like this. However, if we look at the decimal expansion of pi, this is equal to 3.1415, etc. But notice how there's no repeating pattern in the digits of pi. The rule is, if there is a repeating pattern eventually in the digits of a number's decimal expansion, that number must be rational. But if there isn't a repeating pattern, then it has to be irrational. In particular, if a number's decimal expansion terminates, such as the number 6, which doesn't even have anything after the decimal, then that's equivalent to saying 6.000, etc., which is a repeating pattern. Therefore, 6 is rational by this rule. Some other familiar properties of real numbers are being a natural number. The natural numbers are just 1, 2, 3, 4, 5, etc., the numbers you count with. A whole number, which is the same as the natural numbers except it includes 0 as well. Or an integer. An integer is the same as a natural number except it can be 0 or negative. So like -3, -2, -1, 0, 1, 2, 3, etc. It's actually quite useful to visualize these properties in the following way. Let's draw a large box which represents all the real numbers. Now we can divide this box into two sets. One set for the rational numbers and one for the irrational numbers. And then within the rational numbers, we can have a box that represents the integers. Inside of the integers, we have the whole numbers. And inside of that box, we can put the natural numbers. What this diagram is saying is that a real number can be either rational or irrational, and a rational number can be an integer or it can be a non-integer, but there's no integer that's an irrational number, so the integers are contained within the rational numbers. Similarly, the whole numbers are contained within the integers, so every whole number is an integer. And finally, every natural number is a whole number. Although don't let the scale of this diagram mislead you. There are actually a lot more irrational numbers than there are rational numbers, even though the irrational numbers have a smaller box in this picture. Finally, a very cool property of the real numbers is that it's a field. What it means for it to be a field is that there's two operations, in this case addition and multiplication, and both of these operations satisfy the four properties you're probably already familiar with. That is commutativity, a plus b is equal to b plus a, associativity, a plus b plus c is equal to a plus b plus c, identity, so a plus 0 is equal to a, and inverses, a plus minus a equals 0. And the same properties hold for multiplication if we replace 0 with 1 and minus a with 1 over a whenever a is not equal to 0. And finally, a field has to satisfy the distributive property. So a times b plus c is equal to a times b plus a times c. An interesting fact is that the rational numbers also form a field. However, just the integers do not. Can you figure out which rule the integers break?